Good morning. Till the last class, we have seen that how these the variety different types of dynamic shift registers can be realized using NMOS technology. And the kind of shift register so far I have told you that was 1 bit word for 1 bit word. If you want to extend it to an n bit word, naturally you have to repeat the same thing. Let us see how it is actually realized. For example, all these shift registers, whatever I have discussed so far, can be represented by a block schematic something like this for an n channel or n bit applications. Okay. This is a basic, of course. Here we assume that there is a steering gate at each shift register channel. There is a steering gate and an inverter. But as we have seen that this may not be a traditional inverter, we can realize it using switches also in the ratioless design. In the ratio design, these are ordinary inverters, whereas in ratioless design, they look like inverters, but only thing is they actually behave as switches, so that naturally there is no need of maintaining a ratio. This is what I can call an n-bit half register. N-bit half register, and we shall show it by a block something like this. I will call it R by 2. That is traditional way of writing. Then like this, then like this. So these are the outputs. So x1, x2, x3, xn, and these are the outputs. So this is the equivalent of, you can say that the same n-bit half register can be represented by a block schematic like this, so that I can combine them to form a n-bit shift register which looks like this. N-bit which looks like this. Similarly, sorry, I have not shown the phi. So this is the equivalent thing. Similarly, I have done it. You just see that by suitably cascading form the n-bit in this case, such a design of layout not only along the row but also along the column. For example, all the switches which are to be placed here, they can be placed one after another, and we have a single polysilicon rail for the application of Phi 1. I have a chain of inverters or pair transistors, pair MOSFETs, and inside this there is nothing special. And this, that shift registers are very, very important tool. Without shift register, you cannot really perform any mathematical operation. So its realization in the chip form is rather simple, and particularly in dynamic form, where the transistor count is quite less. So in dynamic form, rational design, if you do, you have a very compact shift register performance. This is what is called n-bit word, and it can be, that the length can also be n bits. It depends on the applications. But as you know, there are many shift register applications where we need some kind of data is called data path or pipeline data structure. In the case of data path, half stage of a data path half stage of a data path you can represent like this. Then it goes to a functional block for performing a combinational logic function. So I'll call it a CL block, combinational logic block, and it is actuated by the control signal. So I'll call it control, and then you get the output. This is what is called known as the half stage of a data path. So just by combining, cascading them, you produce the full pipeline data structure as indicated in this case. That is nothing but the repetition of the same thing while cascading them. Here you see that already R1, R2, etc. I have not shown. This has to be connected by Phi 1, and just while and this is for control signal. So every at the output of each half register we have a combinational logic, or that combinational logic to perform a certain functions, and thereafter it goes to the next subsequent half stages, so that you get a pipeline data structure. So finally the pipeline data structure becomes like this. NMOS, CMOS, I am writing NMOS, but it is not restricted to NMOS or CMOS. Anything sequential, this is used in sequential AC, sequential machines. So it is simply the structure, repetition of the same thing which I have drawn. So this continues. And you have got the phi 1 here and definitely phi 2 here and so on and so forth. And you have the different controls here. This is one control, input control. Similarly, this is the next input control. It comes from other parts of the circuit. So a typical pipeline data path, which is very very common in any microprocessor architecture or any kind of function, the digital circuit, digital ICs, it looks like this, where we make use of the half resistors interposed between the combinational logic blocks as indicated here. This is for n bit, okay, for sequential machines. This has got major application in sequential machines. So whatever the shift register, whatever discussed here, the register has a versatile applicability in digital applications, and this one today, particularly in the clock mode, we apply in this in the data path like this as indicated in the diagram. In all these applications, a ratioless design, ratioless compact design with very low power consumption, that is the thing we have already observed, that because everything is performed by clock, the power consumption is automatically reduced to very low value. And so that's how we can, even the MOS technology, we can reduce the power consumption as well as speed, power delay product to a very low value using this kind of concept. Now this is, so far we have discussed only the shift registers, but the same concept of that the dynamic logic can be applied to realize any standard logic function. For example, that is what is known as Precharged logic concept. Precharged logic. Advantage is here that you can have synchronous operation. You can have synchronous operation instead of asynchronous. Synchronous operation, there are a lot of advantages enough, but from timing point of view, and for any synchronous operation, we prefer to use Precharged logic in place of standard static logic. What are they? It looks like this. We just take the standard kind of inverter structure, but it is not exactly an inverter. Exactly similar thing I have discussed, but it is a little bit different from that. In this case, you see that you see that the steering gate, that the pass transistor at the input, it is driven by a clock phi 1, whereas the adjacent load transistor, if you call it a load transistor, it is driven by another clock phi 2, and these are two non-overlapping clock pulses. As indicated earlier, these are pulses are like this, clock pulses are like this. So phi 1 and phi 2 are like this. Non-overlapping two-phase clock pulses. Non-overlapping two-phase clock pulses. Non-overlapping two-phase clock pulses. Now, in this case, we normally speak of two phases of operation. One is called precharge phase, for which phi 2 is high and phi 1 is low. And the next phase is called evaluate phase, for which phi 2 is low and phi 1 is high. Okay? You see that when phi is high and phi 1 is low, this transistor is off, whereas this transistor is on. This transistor is off means this transistor, the so-called driver transistor, may be off or on, depending on what voltage it was there at the earlier, just at the earlier cycle. So it may be on or off, does not matter. But this transistor is on. Okay? And then, as you are making phi 2 is high, because you see the phi 2 high and phi 1, so this transistor is on, and you can arrange in such a way that phi 2 magnitude is a little bit more than VDD, so that this remains in strong linear region instead of saturation. If phi 2 and VDD are the same, as you know, the problem of that output will not be charged fully to VDD, rather it will be charged to VDD minus VT. But if phi 2 is VT more than VDD, as you have seen, at least VT more than VDD, it will remain in linear region, and this transistor with this output will charge to the full voltage VDD. So when phi 2 is high and phi 1 is 0, the output node is charged to VDD. That means whatever capacitance is associated between this output node and ground, that will charge to the full voltage, and it will become high. That means output will remain high, become high and sustain high till this condition is maintained. But as soon as phi 2 becomes 0, this transistor is off. Because you see that normally the pulse widths are small compared to the pulse repetition period, pulse period. So naturally, for most of the time, these two transistors will remain off. Only for some short time intervals, these transistors will become on and off depending on the sequence, whatever I have applied. So after this phase, after the precharge phase, for some time, both the transistor, both phi 1 and phi 2 are 0. So both of them are off. But then phi 1 becomes high in the evaluate phase. Phi 2 remains 0 because of the non-overlapping clocks, but phi 1 becomes high. Now what is going to happen? Whatever input is there, that will now be transferred to this point. And according to that, this output will retain the charge or it will be fully discharged. Please remember, output was charged to a certain voltage, VDD. I am not calling it 1 or 0, because this is during the precharge phase, which is not countable during the actual logic functioning. Actually, logic function, we shall see that, yeah, it is functioning when it is in the evaluation phase. In the evaluation phase, phi 1 is high means if it is 1, it becomes 0, means this becomes short, this transistor becomes heavily conducting. Whatever charge was there, that will be discharged, so it will tend towards 0 volt. On the other hand, if input was 0, this transistor will remain off. That means the charge will be retained here, and 1 so it will behave as an inverter. This one will behave as an inverter, typical inverter, during the evaluate phase. Precharge phase, why we do so? Simply because of synchronous logic. I want to do the same thing in synchronization with certain clock signals. I do not want to do it arbitrarily in a sequential fashion. I want to do it, work it, as you know, in any synchronous logic, I want the entire logic system, entire digital IC or digital circuit should work in synchronization with certain instructions from certain, just like, that in a guided class, it is the teacher who guides. But if there is no teacher and if everybody, say in your examination system, or if there is no invigilator, there is chaos, as you know, everybody do that, but the invigilator maintains some discipline. Here also the clocks are trying to maintain that discipline so that the logic works without any problem. There will be no problem of timing, particularly, as you know, in big circuits. I told you the timing errors are the more important, very important things. And in synchronous logic, the time, but problem is, as you know, that the speed of operation has to be limited. You have to supply clock everywhere. The speed of operation will be limited, packing density will be limited. Those are limitations, but otherwise synchronous logic is very good. And for those applications, this kind of inverter, rather than plain inverter, ordinary inverter, is preferable. The same concept now can be used for realizing any logic gate. Let us see any logic gate. For example, NOR gate. What I do simply, I take so you apply your A here, apply your B here, and this is all phi 1. Then at this output, you get A nor B after only in the evaluate phase. As before, only in the evaluate phase, you get A nor B at this particular point. As before, you can easily find that when phi 2 is high and phi 1 is low, this is what is known as precharge phase. During this, the output node is charged to the full voltage VDD. But then when phi 1 and phi 2 both are 0, most of the time it happens. This is isolated. This point is isolated. And therefore, that output point, it is retained. It is retained. And thereafter, as according to your inputs, whatever way you connect the transistor, in this case we have connected the transistors in parallel, in shunt, so that we get when phi 1 is high, phi 2 remaining 0, that A nor B operation, A nor B will be available at the output only during the evaluate phase. Therefore, in the same way you can see that exactly it is the same as the ordinary static NMOS logic. Only thing what I have done, I have connected the clock with the load transistor, and all the transistors in the driver, the way you have connected, you remember that if you connect them in parallel, we get NOR. If we connect them in series, we get NAND. If we make a series parallel combination, we get various combinational logics implemented. Only thing is, at the input of each, I have to put a pass transistor. And all these transistors have to be driven by a clock phi 1, which is a non-overlapping two-phase clock with respect to phi 2. Okay? So this is that way. Therefore, you can, the example I have given for NOR gate, so you can realize any logic A plus B, A and B, A, NOR, any combinational logic, whatever I have. The only addition thing what I have done, I have connected these transistors here, which were not there in earlier case. And I have not just connected it like this or like this. Normally, this is either connected to this or depending or to a VGG supply. But here also I have connected another clock pulse. And this is this clock and this common clock. They are two-phase non-overlapping clock. That's the thing. And by using this thing, you can see that we can very easily realize P-charge multiplexer. For example, multiplexer. So this is the example of a clocked multiplexer or a Precharge multiplexer, whatever you call it. In this case, what we are doing initially as before, when phi 2 is high, and these are all non-overlapping clocks, please remember that. When phi 2 is high, all of the other clocks must be 0, non-overlapping. So when phi 2 is high, you know that this point is, as before, is Precharged to VDD. Then according to whatever, when phi 1 comes, these two are off, this signal comes here and you get, you know, the inverted version of whatever data available here. Similarly, when this is high, you get the inverted thing of whatever, exactly the same thing. So this is nothing but a simple multiplexer circuit. The multiplexing is performed by the clocking scheme. At what instance you have to? Huh? That I'm not sure. Yeah. That I'm not sorry. I should have shown. Actually, if there are dots, etc., that might be there. And oh, I see. I have just sorry. I have drawn it just opposite wrongly. I have drawn it wrongly. These links are to be removed. These links are to be removed. You are right. These links are to be removed. In the same way, we can have a, is it all right? In the same way, we can have a Precharge data bus. Like this. Where the different sources may be say registers, the outputs from registers, maybe some functional blocks means combinational logic outputs, ALU, etc., and various other functional blocks available on the chip. As you know that they have to be combined. Sometimes we have to combine them and get an output like this. So this is a common data bus. The difference between this one and the other one is the one which I just now discussed. Here you see that I have got independent clocks, but in this case it's driven by the same clock phi 1. Same clock phi 1. Only thing is I want to suitably combine the signals or the digital output from the various sub-blocks or various blocks in the IC or in a big circuit. And I want to do it in a synchronous fashion so that the timing failure is not there, timing problem is not there. So what I do, again, I use a precharge during precharge cycle, phi 2 is high, phi 1 is 0. This is charged to the full voltage VDD. Then depending on the source signal, whatever is coming from the various sources, you get the output here. And that is determined by phi 1 is equal to 1. That means during the evaluate phase. These are very standard techniques used in any, any digital IC today.
But sir, if several sources at a time send the same data. They should be clocked by different clocks.
No, it depends on the applications. In this case, I am assuming that the different sources, the output from them have to be combined suitably. You know, that it depends on, ultimately it is a combinational logic, but you have to combine it suitably. It depends on the design. Similarly, we can have different different 511, 512, 513, that depends on the application. It is the same as the earlier one in that case, whatever I have shown in the earlier one, but just a simple different version, that's all.
One source will give the data, sir. Parallelly, many sources of the same data. You have local shorting because if if one of the sources gives a 1 on the bus and the other source gives a 0, yes, you just have a local shorting. Yes.
No, you know that. No, actually, yeah. In this particular, this is an example. You can have various versions of that. You see that 5.1 is 0 means you are allowing the things to settle down to the particular level. Independently, you are allowing each thing to settle down to the desired level. Because when 5.1 is 0, that is the advantage of this. During the precharge phase, the signal comes here. During the precharge phase, you see that the output you get fully charged. But during this time, whatever signal is coming, you are allowing time for whole thing to settle down to a certain steady state, and these transistors ultimately get on or off depending on whatever signal is coming there. And ultimately, suddenly, you are making all of them on, all the parts on in this particular case, and you get the output data from here. Okay, this is a typical example. In this case, single line, yes. In this case, a single line, a common output bus, data bus. It is nothing but combined. There is nothing special in it. You are combining the different things. I want that a function, that is signal from source 1. Here is source 1 is a single one. You know that it is not a sequential data. It is a sequential data in this particular example. Similarly, as I have given you two simple examples, similarly you can combine them suitably to form any such standard data bus. Now let us go to the next topic. Now I think we are going to, because we have very limited time. Let us now consider the applications, for example, to, because more important today is the CMOS. So we shall consider first clocked CMOS logic. Sorry, this is not there. In the case of CMOS, normally, sorry, this is not there. This is usually symbolically shown like this. Only, compared to the static CMOS inverter, this is an inverter, typical example, clocked CMOS inverter. This is phi and this is phi complement. You see that the actual inverting function is produced by these two transistors as usual. This PMOS and this NMOS. This is a driver and this is a load. Where intermediate, I have put a pair of PMOS and NMOS I have indicated here to have clocked operation. When phi is 0, what is going to happen? There is input, some input is available, but phi is 0. So this transistor is off and this transistor is on, off, because this is phi inverse. So the output is now just floating. Whatever earlier stage was there, that will be maintained. But this is not a Precharge-like kind of thing. This conceptual is different. But then as soon as phi becomes high, both the transistors become on, and you allow the function to come, that the inverted form of the inverted form of the input to come at this point. So output will not be, so therefore when phi is equal to 0, whatever output data is there, that is not our actual output. Please remember this. When phi is equal to 0, that means when clock pulse is not there at all, this whatever output, that is don't care type of thing, it is not the actual output. Only when phi makes a transition from 0 to high, 0, this is phi, 0 to high at this point, 0 to 1, then the input will be passed to the output in the inverted form. So now suppose I want to, this is nothing but the clock logic. This is the same thing, but the clock version. Same static logic, whatever functions we could do in the same way, you can use this one. Only thing is here you are permitting this output to go in the proper format only when the clock goes high, not during the period when clock is low. Okay. Now, in this case, what is the advantage and what is the disadvantage? This is a case of simple inverter, but you can extend it to any logic. For example, you are interested in producing a NOR function. What you do? You remember the driver transistor should be connected in parallel, whereas the load, this is the load. Please remember, this is the driver and this is the load. They should be connected in series, and you have to connect common signal, A here, B here, B here. Similarly, if it is a NAND gate, these have to be connected, 2 transistors or 3 transistors have to be stacked in series here, whereas corresponding transistors, load transistors, to be connected in shunt, and the signals to be. Only thing is there will be a common thing. This is the common thing everywhere. This common block, which was absent in the static CMOS. This is an additional pair of MOSFETs, an NMOS and a PMOS, now connected to allow clocked operation. But is it a very convenient way of, is it really much beneficial? Similarly, that you can compare with the Precharge logic case also. Your transistor count is more in this particular examples. Whatever I have discussed the NMOS case, the transistor count is much more than the normal static logic. In this case, similarly here also, if you compare the normal static CMOS logic, do you think there is any benefit, special benefit derived out of it? No, because the transistor count is always two more than the previous ones. And yeah, I am getting clocked operation, that's my main benefit, but otherwise from a VLSI point of view, packing density point of view, I don't get the benefit of the so-called dynamic operation, which is the prime. Why dynamic operation? Why people went for dynamic operation? Simply because of, having a very low transistor count to achieve a high packing density, to realize much complex circuits in the same chip. That is why the dynamic logic concept came. From that point of view, this particular aspect is not at all possible. It is not a beneficial approach that way. Yeah, it can be used in the clock logic applications, but otherwise I am not getting the benefit of VLSI in this particular case. I am sure you have understood that you can realize any CMOS combinational logic by this. Only thing you have to play with these transistors and keeping them as it is. The pair of transistors in the core has to be kept unaltered. Only here you have to, just like static CMOS, you have to connect a number of equal, if there are n transistors here, there should be n transistors here also. Only thing is they are connected in the complementary fashion, just in the complementary fashion. And two more transistors. So compared to static CMOS, what is the transistor count here? 2 into n plus 1, 2n plus 2. Isn't it? Compared, if this is the static CMOS and this is a clocked CMOS, transistor count, in this case it is 2n, and in this case 2n plus 2. That is 2 into n plus 1. Only advantage gained is that it is a clocked operation. So there are some advantages in it. But you know that people try to realize not only try to have not only clocked operation but also high packing density. And from that point of view, the new concept came, which is called Precharged CMOS logic. This is clocked CMOS logic. The other one is called Precharged CMOS logic. Precharged CMOS logic. Here you will find there are a lot of advantages. In this particular concept, there are a lot of advantages. This VSS may be ground. I am showing VSS, but in general may be ground and 5 volt or like this. It depends on applications. You see that I have just interchanged the position of the clocked transistors and the driver transistor responsible for the inversion or for the logic operation. What I have done here, you see, the two outermost transistors, the PMOS and NMOS, they are, you know, I don't apply phi and phi bar here. You please remember, you compare in the earlier case, I had to apply phi and phi complement, but that I am not doing here. I have connecting the same phi, and this is one transistor intermediate where at the gate of which this is an NMOS. Please remember, there is only one PMOS and the rest are NMOS. I am applying my input voltage, and here from I am getting the output voltage. How does it work? This is again a precharge. You can easily find the precharge logic. This is a precharge CMOS inverter. This is an inverter, simple inverter. When phi is 0, this is off, this is on. So the output gets charged to VDD, and this is what is known as Precharge phase. So Precharge means phi is 0. Phi is 0 means Precharge phase. Phi is 0 means, you know, this transistor is off, but this transistor is on. Compare the earlier case, here I had to connect phi and phi inverse, but that I have not done yet. Same phi. So when phi is 0, this transistor is off, this transistor is on, and as a result, this chain is off. From here to ground or VSS, this chain is off. So this point is floating now, and it is getting charged through this transistor which is on to VDD. So the output node is charged to VDD. And then when phi becomes in the evaluate phase, phi becomes 1, This becomes 0 now. This becomes off now. In the evaluate phase, this transistor is also power supply is isolated now. And whatever things have happened here, in this case I have shown only one transistor. There could be a block of transistors here in this place that I am showing. Instead of one transistor, there could be a block of transistors with different signals at the inputs. Okay, so during this precharge time, phase time, you have allowed sufficient time to settle this block to certain on-off states. All the transistors in this block, here I have shown only one transistor because it is a simple inverter. In this case, this transistor you have given allowed sufficient time so that the gate of this transistor has assumed the proper level, either 0 or 1, and this has created a situation to get turned or on or off. If it is high, it is turned on, low, it is turned on. But because this transistor remains off during the precharge phase, nothing happened here. Then in the next case, when the evaluate phase, now the power supply is decoupled because this transistor gets off. Phi 1 is 1 means this is off, this is on. Whatever happened here, because this is a ground path, that will be reflected at the output in the inverted form. If you have combined them in the switching mode to produce a function f, you will get f inverse here. Okay? And that is what is called evaluate phase. Similar way you can draw the circuits for, for example, a NAND gate and a NOR gate. There are great advantages in it. So, okay, so you see that this is a circuit where instead of one transistor I have got two transistors in series. Naturally you get NAND operation here during the evaluate phase when phi goes high. Two transistors here are in shunt, therefore you get NOR function here during the evaluate phase when phi is 1. So what is the advantage gained now? Not only it is a clocked logic, but also you see that you have to managing the whole thing using one single PMOS, which is the most troublesome thing in CMOS technology. You have to have an in-well for that. So for performing this logic function, whatever complicated it may be, you are using only one PMOS. And has its purpose been served by using only one PMOS? What was the main purpose of using a PMOS in CMOS technology? To reduce power dissipation. Standby, that is happening. Because this transistor is located in the pull-up side and it is getting clocked. So if you just compare the transistor count for the static CMOS, clocked CMOS, and precharge CMOS, can you tell me what is the benefit? Here in this case, what will be the transistor count? Suppose it will be simply n plus 2. Simply n, and this is the n number of transistors here required for that function, and then plus 2. Earlier case it was 2n for static CMOS, 2n plus 2 for clocked CMOS, and for this case it is only n plus 2. So there are a lot of advantages so far as VLSI applications are concerned, packing density is concerned. Naturally speed will also, because you can that less transistors means there will be less interference, less parasitic effects, and which results into a higher speed. And power dissipation, no problem. Even just one PMOS is serving that purpose. Sometimes some people prefer to call it a pseudo NMOS. Though pseudo NMOS is not exactly this. There is another name, another branch of MOS technology called pseudo NMOS. But this is not exactly pseudo, but you can call it pseudo NMOS also. We shall discuss in the next class that what is the drawback of this. That it appears very simple.